So what slide did we stop on? Path difference, wasn't it?
Yes.
We did this last time.
We stopped here. I think.
Yeah. We remember discussing path difference. Do you remember one application of path difference that I was talking about?
The headphones.
Yeah, something else though.
Sorry, we went to the other classroom.
Like a pair of idiots, huh?
I was following him and he was following me.
Yeah, okay. So who was in the other room?
Business.
Alright, and you looked around and said, this isn't right.
Yeah, I was like, we multiplied.
Okay. Well, you didn't miss anything exciting. We're just trying to remember, what was the example I gave you of an application of path difference? Do you remember? No, I don't remember an application of path
Oh yeah,
difference.
the CD.
The CD. The CD.
Which is not even used anymore.
No,
Well,
no,
Blu-ray.
no. Blu-ray, yeah, that would still be the same technology, I would think.
Everything's changed
Now,
now.
the Blu-ray has layers to it, I think.
I've never understood.
Yeah, I think the Blu-ray has layers to it. So
It can hold so much more.
yeah. So
And they are standard.
I'm not sure if there's some kind of also, in addition to the path difference, if maybe there's some kind of focus effect where it focuses in on different layers. I don't know. Anyways, we'll continue from here. I'm trying to think of any other use of path difference. So, constructive interference, what would that mean?
Like it adds on to it.
Yeah, the waves combine to form a bigger wave, and destructive,
Cancel
the form a smaller wave. Completely destructive,
cancel each other.
yeah. So you need these three definitions or terms.
This is from interference.
Yeah.
The next
Yeah, part 2. You can't see Gina, or you just need more time? Yeah. Well, it's no rush, I can wait. Okie dokie.
last one.
It's alright, Jack. Okie dokie. We were talking about examples of each of these. So, constructive interference, I think, a good example is when maybe two ocean waves come together to form a bigger wave, or something like this. Destructive interference, we talked about last time. What was the example we had of this? Destructive interference. Yeah, the noise cancelling on the headphones. That's a good example. Now, completely destructive interference is very difficult to do, but in some situations it's possible. I think when we talk about an airplane, I think we could say that's completely destructive interference. So I want you to think about something for a moment, something I always think about. When you see a plane flying low in the sky, you can clearly hear it, right? So that must mean the engine is extremely loud, because you can hear it, 2 kilometers away, okay? So you would think if you were sitting in the plane, then that must be painfully loud, because you're only 10 meters from the engine. But it's not. You can have a conversation and you can watch and read and all this. So I don't know. I think the technology in planes to cancel the sound of the engine must be very impressive, very well designed.
Do they do that with active, or is it just noise cancelling?
Yeah, I do wonder. I do wonder about that, or if it's both. If it's both, I would think most of it is probably in the design rather than active.
Okay.
But I'm seeing a trend now for cars to have active noise cancelling inside it,
Yeah.
so you don't hear the engine as much. So it seems to be a normal thing now. But like I said, completely destructive is going to be very difficult to do. You can only really do it if you have a sound that's very repetitive, like an engine sound, or you know. I think this was first used in factories. They would play a cancelling wave on the speaker system, cancel the sound of the machines. Yeah. Okay.
I just have a question.
Sorry, just before I go on, there's an example of completely destructive and then constructive. Yeah.
Wouldn't that be bad for your ear, for your ears at long run?
Which one?
Like noise cancelling?
No. The wave cancels with no side effect. Yeah. It's as if there was no sound to begin with.
Okay.
Yeah.
Is it completely constructive?
Yeah, I was wondering that. I'm like, not really. Maybe two identical waves adding together. Yeah.
Like if you have two separate speakers. With
Yeah. Yeah, it would double the energy, but because of how the human ear works, it does not mean you will perceive it as twice as loud.
Yeah, it doesn't sound.
Yeah, so having two speakers is technically twice the energy and twice the amplitude, but you will not hear it twice as loud as having just the one speaker on. It's the same effect with lights. You know, we have two lights on here, and if I turn on two more lights, it doesn't seem twice as bright. It would only seem maybe 40% brighter. It's just how the human senses work. Now that's a good thing, because it means if I was to half the lights, it means it doesn't seem half as dark. And that's the important thing here. You can still see quite well as the lights go down. Do you know what I'm saying? Yeah. Okay. Now, this is an important experiment. It's called Young's double slit experiment. It's a classic experiment in physics, and it's very common in the exam. And it's a very, very, very simple experiment. What you have is a light source. Now, it needs to be what's called, monochromatic was usually a good one, but I don't think it has to be. But anyways, usually it's monochromatic light, meaning light of one colour, like a red light or blue light or whatever. And then you pass this light through two slits. Now the effect of doing that is, if you have a light source, the light wave comes out and it hits the slits, and then it makes two smaller waves that come out here. So really what you've done is you've made two sources of light. But what's brilliant about this is that both sources, they are coherent. Do you remember coherent? Coherent means same phase difference and the same frequency. Now, in fact, the phase difference here will be zero. They'd be identical waves, and the frequency will be identical.
To the parent wave or to the two smaller waves?
To each other. Yeah. Because you talk about phase difference as comparing the crest with the crest here. Okay? So this wave spreads out. Now, what I'll do is, as the wave spreads out, I'll use green to represent crest and red to represent trough. So go crest, 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 and crest like that. And then here, crest, 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 crest like that. So I really kind of need one more here, sorry. bit messy. So can you see here, two crests have combined. So the new crest will be bigger or smaller?
Bigger.
Bigger. So what you'll have here is a bright light here. But let me add in the troughs now, which of course would be in between the crest, wouldn't they? So let's take this spot here. Can you see right here? What is going to happen there? A crest of one wave will meet, it will meet the trough of another wave, and so the waves cancel. The light has now vanished. So if you were to look at this part of the screen, you would get no light here, because as this moves in, there's nothing there anymore. So what you'll discover is you'll have a very bright spot here in the center. Then you'll have darkness. Then you'll have another bright spot, but it's not as bright. And then another spot here, but again, not as bright. And the same on the other side. You'll have a bright spot, but not as bright as the center. Another bright spot, but again, not as bright as the center. That's the image you see on the screen here. Now, you can't really see it here, but the center one is brighter than the neighbouring ones. Okay, this is called an interference pattern, a fringe pattern. That's what this is called. So I'll just write some names in here. So what did we say? These are two sources of light. And how did we make two sources? Well, we used one source. And here this is called a fringe, or in other words, an interference pattern. And this one here in the center is the brightest. And we usually call that one n equals 0. This one here, less bright. We call that n equals 1, n equals 2. And this one here? Minus 1 and n equals minus 2. Okay. Now, what you can have here, we have a cancel. And then what did I say? Like, for example, here, what's happening here? They add. Yeah? And yes, this is called Young's experiment.
Same as Young's modulus?
No, I don't. Wait, actually, I don't know, because well, they might be. I mean, how many people are going to be called Young? It would be an amazing coincidence.
But one for materials and one for properties of light.
Yeah, but I'm thinking about the time frame. Both these experiments will be done around at that time, the 17th century. This experiment is kind of old. Would have been around the time of Newton as well. And also, the study of materials was started with Hooke and Hooke's law. And again, he would have been a contemporary of Newton, also 17th century. So the time frame does work out for it to be the same person. Now, we'll need to talk about this experiment more because it's very common in the exam. What we will do in a moment is we'll write down formulas for calculating things like the distance between these fringes and so on. Now, this is an experiment you need to know. However, in the exam they don't usually ask you to describe this experiment. Instead, what happens is they usually give you this experiment as a question and they ask you to calculate things about the experiment. Okay? But still, maybe one year they could decide to do it opposite and ask you to describe the experiment. Okay? So I need you to copy this down as best you can. How to do that, I don't know. With great care, I would say. So is the experiment clear? It's a very simple experiment, isn't it? You just need a light, a card with 2 slits, and a screen. You only need 3 things. Light source, a double slit, and a screen. That's all. In a dark room.
So, the speed of light is the fastest speed possible in the universe. What is the speed of dark?
What do you mean by dark?
So if you had a light, say, projecting a light year away into something, and you had to put
same, speed of light.
Yeah, but wouldn't the darkness appear away?
But is
As if,
Would it appear?
yeah. Well, no, I'll give you a better example, okay? So imagine
Well, it's the same.
the sun suddenly disappears right this second,
Oh,
precisely this
it's
second.
Still,
How long
yeah, until it's dark.
until, no, not until it's dark, until we leave the circular orbit, which is a different thing. So you understand that you'll have to wait, you'll have to wait about 10 minutes before you can see the sun is absent. But you might say, well, there's no gravity force anymore. So couldn't you feel instantly it? And the answer is no. Even the gravity force will only travel at the speed of light. So you cannot violate this law. You cannot get something from point A to point B faster than a light source could. So you might think, well, what about if I do something like you said, like I cover up a light source, or I have a planet and I suddenly remove the planet, you know. And the other example that was realized by Lorentz is, imagine you have a really long stick, and the stick pushes something here.
And it would only travel at the speed.
So we're only traveling at the speed of light.
Sound, yeah.
No, light actually. So you might say, okay, well if I push here, doesn't this instantly move?
Yeah.
Because it's a rigid structure. And the answer is no. If I push here, what you're not realizing is that effect has to travel at light speed to reach here. Not something we can perceive on a human scale. The consequence of this that Lorentz realized was that as objects move faster, or as objects move near the speed of light, a consequence of this result is that they actually begin to contract in size. They start to appear shorter.
So that pen
It's as if it's contracted.
was contracted while you were
You're pushing it, exactly. Yeah. Yeah. It's complicated stuff. How's that picture going? Oh, not bad, not bad. Now, I think in the exam, you wouldn't need to draw all these waves on the diagram, but maybe you want to draw, 2 or 3 to get the point across. No colours, Lynn? All the same colour?
I'm using dash.
Oh, okay, fine. Did you have a good Chinese New Year? Did you celebrate? Yeah? You went to a party, or what did you do?
Just the festival. It was quite small.
Was it?
Yeah, but it was full in the afternoon, but then it gets really empty.
Quickly, doesn't
Yeah.
it? Okay.
But there was some interesting stuff.
Performance?
Performances are by children, but they're
Ah.
actually
Okay, that's something, I suppose. Alright, have you got that? Continue, guys? Or do you need a minute?
I'll show it later for the video.
Will you? For reals?
I
okay.
Okie dokie. Continue?
Mm. Okay.
Yeah? Yeah? Okay. So, if 2 in-phase coherent waves are emitted from 2-point sources and then later superposed on a plane, we find that the waves produce an alteration of max and min. Bright, dark, bright, dark. In other words, if the 2 waves were light waves, we would have bright and dark, bright and dark. But instead of having light, imagine I have sound. I had a sound wave. What would we see happening on the screen if it was a sound wave? It wouldn't be bright and dark.
no sound.
Yeah, it'd be loud and quiet, wouldn't it? Same idea. This type of pattern is known as a 2-point source interference pattern, or just interference pattern, which I think you wrote that word down, didn't you? Interference pattern. And I've already drawn the diagram. Now, I can't do it in this room, but I used to do it in one of the rooms where we had 2 speakers. And I would play a sine wave, a sinusoidal sound. And then I would have students walk across the back of the room. And they could hear the sound getting louder and quieter. It's quite interesting. So if you just sit here, you would just hear constant volume. And then as you walk along the back wall, it would go up and down. So I can't do it here. I would need to have 2 speakers and I could do it. It's not difficult to do. And then I just go to YouTube and type in like sine wave sound or something like this. And that would be it. Yeah. Okay. And the description of the experiment, I mean, I don't have to write it down. What equipment do you need? What are the 3 things? Light source, screen, double slit. Yeah? And what do you do? Put the light source, put this double slit between the light source and the screen and observe the result in a dark room. End of experiment. Okay. Back in the day, you could get experiments named after you for quite simple things. Not anymore. Okay. Now, a diffraction grating. Does anyone know what this is? No?
It's like depolarized.
No, not depolarized. It's basically a piece of plastic with just many slits in it. I'm going to give you a picture of it. Can you see here?
Oh, yeah.
You have a piece of plastic and you have many slits in it. So what happens is, imagine this is it here. The light comes in, and it doesn't really matter where the light is. What's nice about this is it will eventually have to hit somewhere where there's 2 slits and spread out. Because you realise in this experiment it's going to be quite difficult to get the light exactly in the middle of the double slit, right? Like, I mean, to be really precise. But if you just use something like this, it doesn't matter. As long as the light hits somewhere on this, it will split through 2 holes. You might say, well, why won't it, will it split through 3 holes? No, if the light is narrow enough, it can't spread over 3 holes, it'll spread over 2. So this is called a diffraction grating, and basically you use it in the same way you use the double slit here. Yeah? And what happens is you buy these, they're quite cheap obviously, and it might say something like 600 slits per meter as the measurement. And if you want smaller holes, then you'd have something like 1,000 slits per meter. Okay. I think all I would like you to do here is just write down diffraction grating and draw a picture of this. Its purpose is to be the double slit in the experiment. Do you understand, Zach? Do you? That was a long pause before you said yeah. Maybe.
How would it become 2? Would it be more than 2?
No, you have to use a narrow beam of light.
So,
Obviously, if you shine a flashlight on it, you'll get but narrow, like a laser pointer.
Okay.
could you use one of those for zooming?
No,
No?
no.
Because I saw
It's-
somewhere that they made some like glasses, like quite cheap, with those kind of things, like small, super small.
Ah, yeah.
Did you saw that?
I had one.
Yeah.
You had one?
Actually works
With
like
the slits,
like if you
Ah,
can't
like
see
like
anything.
Kanye West or something.
Kind
No,
of
like
super-
sometimes when you can't really see anything and you do from a small
Yeah, you
thing,
do
it
like-
gets clearer.
Yeah.
Weird.
Yeah.
I don't think there's any physics principle there. I think this is more of a psychological principle.
So,
No?
for example, if I
No.
take off my glasses, I can't really see the screen.
Yeah.
If you
And
do
then
it
I
from a
can
really
now.
small
Yeah,
place,
yeah,
then you can, like really, really small, like around
yeah.
this
If
size.
you do that.
It's a slide technique.
Yeah.
Oh,
When you have your glasses back.
you're focusing in on a smaller spot.
Yeah.
Okay. And you're saying like you have glasses where they have.
They
Like
made
multiple
kind of
spots,
with
and then
that
when you put it like
thing.
this, you can see things more clearly.
Interesting.
Still can't read.
No, you can only use it for like, let's say, you just need to know where you're going.
Yeah.
That kind of thing.
Interesting.
If I lost my glasses, I would have to walk everywhere like this.
No, just use your phone like this. Use your phone.
If you have 20/20 vision, you won't notice the difference.
No, I guess these. I guess the text is a little bit sharper. Yeah.
You see?
Life hacks by the engineers. All right, have you got that? Yep. Okay. Now, some terms in the experiment. So the slit separation D is the distance between the two sources. So we call this distance here the slit separation D. The fringe separation, that's the distance here. We call this, I think I used the letter X for this one. No, sorry, S. That's the fringe separation. Between the spots, yeah. The angle, theta. Well, that is now, it depends on which fringe you're looking at, which point you're looking at. So for example, this one here, that, I guess I could call that theta 2 if I wanted to. And for example, this one here, what would you call that one? Theta 1. Yeah, for example. The theta is the angle. Distance to screen, well, that's obvious. That's going to be this distance, isn't it? I think I use a capital D. And the order is N. That is these guys. They're called the order. The position. Okay, I'll give you a minute to write that down. You can either write this down or add it to the diagram, whichever you prefer. Is today a shawarma day or a burrito day?
Burrito all the way.
Burrito day? Don't know. I think I'm hungrier than a burrito. I'm also thinking, is it a coffee and cake day as well? Going all out.
So would the two, like N1 and N-1, would the intensities be the same at N1
Yeah, it should be symmetric.
and N-1?
Yeah, it should be symmetric.
But what if, are we always assuming the light source is in the middle of the two slits? So it's
Yes, yeah.
Okay.
And that it's perpendicular to the screen and all that, yeah. So you have a completely symmetric right angle picture.
So the light source would be a D over 2.
Yeah, but I don't talk too much about that because it gets a little bit messy. Because I totally fluffed over the fact, because I have to look it up, because I don't know it, because it doesn't really come up in the exam. But the D, is it the distance between the center of the slits or the distance that is blocked in the middle by the two slits? Which it is, I do not know.
It makes sense because
Did you not learn anything about Lorentz contractions? Nothing in physics has to make sense.
conjecture.
Any of you guys watching the Trump trial?
Oh, no.
The
Because because of the time difference, it means the trial begins every evening at 6 p.m. So as soon as I get home, it's on.
Where do you watch it?
CNN.
CNN?
They have live coverage of it.
CNN, hard-hitting memes.
What? I don't know this meme.
the normal is in the middle, right?
The normal?
Like,
Oh, yeah, it's the line from the center perpendicular to the plane. Basically the n equals 0 line.
oh, okay.
What does that mean? Plus minus nth?
Plus or minus the nth position. Like first, second, third. Or minus 1, minus 2, minus 3. You call, Gina? A little? Maybe you need a burrito or a shawarma today. Or a pizza. Right, you got that? Not yet? What class did you have this morning? Chemistry. And what are you doing in chemistry? Still organic chemistry, right? Is it tricky?
Just a hassle with all the names and all the combinations and the things they can put in.
Yeah. All right, you got that? Yeah, continue, Diego. Now, when it comes to the double slit situation, we have two formulas. That's all, just two. So, they are, now before you write them down, let me just explain them. This one here, n lambda equals d sine theta. This formula is normally used to give us the theta, the angle that we're looking for, usually. Okay. And this one here, S, if you remember from my picture, that is the fringe separation, and that's lambda big, the bigger distance over the smaller distance. The distance to the screen divided by the slit distance. Yeah. Now, you'll notice that one of these is an equal and the other is an approximate. Let me explain why. Technically speaking, the distance between these is not constant. In fact, what happens is, as you move out, they become further apart. Now, what this formula is doing is giving you the rough average distance between them. Okay? But technically, that's wrong because the distance isn't constant. It's getting bigger. Yeah? Now, in the exam, that doesn't bother them. They use this formula in the exam as if it was an equal, which I find interesting. So, for example, if they said, what is the fringe separation, then they're imagining that it's a constant separation, and so you can use this formula. Okay. Now, what's more interesting is, suppose they ask you, what is the distance from 0 to 2? Well, there's two ways you could do it. You could use trigonometry and use this formula, get the theta, and draw a triangle. Or you could use this formula and then multiply your answer by 2. Which would be the more accurate way of doing it?
Doesn't that?
Well, before, yeah, which one would be more?
Doesn't include the distance of the
line.
of the light.
Yeah, because there's gonna be also a light in between, right? There's gonna be a dark slit.
Yeah. The question would be, what's the distance from here to here on the screen?
And
Yeah,
then
but
it's like
wouldn't
1, 2, 3, 4. There'll be
Huh?
three in the middle then. Just a light. Because
Wouldn't
if it's
it-
like a stripe, wouldn't it be around the same distance?
What?
The,
I'm sorry,
The
I'm
light
trying-
wouldn't be over an area of 0 meters. It would be
Yeah,
spread out.
Okay.
So the
Oh,
S
okay,
in
fine.
between, yeah.
Fine, okay. The distance from the center of this intensity to the center of this intensity. Is that better?
Is that the fringe separation?
Oh!
Yeah, because
I understand.
Thing occupies that.
Again, this is something I don't know. Because in the exam, they treat these as if they're just dots of no length. Oh, I'm sorry, you're picturing them as being kind of fat.
Yeah.
Yeah.
As the picture.
Like the picture, yeah. We kind of imagine them as, like when you actually do this experiment with a little laser light, you just get like little pinpoints on the screen. Yeah, okay. This has never happened before. I've been teaching this for a while and no group has ever taught it confused like this. So, anyways, back to my question. If it's a point to point, you could draw a triangle, right? And calculate this angle and then use a little bit of trigonometry. Or you could use this formula and multiply the answer by 2. Which do you use? Depends on the context. For example, imagine the previous question was determine the angle to the second order. Well, then obviously they're trying to get you to use the first one. But imagine the first question was determine the fringe separation, and then the second question was what's the distance to the second order. Well, then they're obviously hinting at you to use the second formula. Yeah? Now we'll have a look at some examples. If you can write these two down. Also, note, I am not 100% sure if these formulas are in the formula book. They're not always in the formula book. The second one might be, but the first one may not be.
So the unit would be
For which?
lambda.
Well, let's look at this. The n has no units. The lambda,
Nanometers.
yeah, nanometers, and d would be nanometers as well.
And so it would be meters. Meters squared over meters.
No. For which letter?
Fringe separation.
Oh, you're looking at the second one.
Yeah.
Oh, yeah. No, it'd be meters squared over meters. Yeah, also known as
Meter.
meters. Yes. All right, continue. You got that? Yes, Dorian.
Okay.
So does frequency play no role in?
No, it does, because the frequency affects the lambda. High frequency light means low lambda. Low frequency light means high lambda. You could rewrite this formula to have frequency in it, Zach. What would you replace the lambda by if you're using light? Guys, if I want to write this formula in using frequency, in terms of frequency of light, what would I replace the lambda by? C over F. Yeah. And if it was sound, it would be the V over F. The speed of sound over F. Yeah? Are you okay, guys? Is this okay? Yeah? Right. I have 2 stinking long questions to do. Okay. A speaker is inside a room. It is humming at 2 kilohertz. There are 2 doors beside each other into the room. They are 1 meter apart. Let me draw the picture. Speaker. 1 meter apart. Sound is coming through here. And this is a hall. Okay.
Why do you have 2 doors like that, a meter apart in a hall?
It's a fancy old building, okay? A boy walks down the hall with the doors on his left. He noticed that as he walks by the room, the sound from the speakers get louder and quieter. He is surprised because he's expecting the sound to get louder, then quieter. The hall he is walking in is 2 meters wide. And the frequency, what did we say it was? 2 kilohertz. And the speed of sound is 330 meters per second. Now what will happen here? Well, we'll get the same story, won't we? We'll get loud, quiet, then loud, but not as loud, then loud, but not as loud. Like this. Yeah? Do I tell you how fast he's walking? No. Right, so the few questions I have is, the first one is I want lambda. The second one is I want this distance here, S. The third one is I want the angle to the second order fringe. So can you see that's this angle? I want theta 2. D. Now you'll have to think about this. What is the maximum order? And I give you a little hint. The theta is always less than 90. Why would it be silly to say the theta is equal to 90?
Because
Yeah, it wouldn't hit the wall, so it's meaningless. And then lastly, how long until the boy no longer hears the humming?
How long what?
As in distance, sorry. So I want to know for part E, basically, for what length of his walk will he be hearing sounds and then no longer hears them? Obviously, he's not going to hear this forever. So I want to know the distance he walks where he can hear this. So, okay, these ones are easy, but then it might get a little hard here. Now, I'll give you a minute to calculate this and then we'll have a look at it. All the information is on the diagram here. Let's see if you can get this. So it's on the screen here, Diego, 3:30. Now, how are we doing? Which part are you on, Zach?
The 8 max.
Good, okay. Which part are you doing, Gina? Oh, good. Okay. We'll do the answers in a minute. Okay. So the first one, I hope you got it. This is just the formula V over F, isn't it? So what did you get for lambda? 0.165 meters. And then S is lambda D over D, isn't it? And what did you get for that? Probably something small as well. 0.33 meters. Now, to get the T to 2, you have to use the first formula with n equal to 2. So, what did you get for T to 2?
0.3363.
Are you in radian mode, man? Come on, you should have known that that was wrong. Right, what is the correct answer for T to 2?
1926.
That sounds more reasonable. What did you get?
19.
19 point...
No, I got.
1.2688.
Oh,
I
you used
got
the previous answer.
I got 18.26.
Yeah, so we can see now already that there's a small difference between the two formulas. Oh, I understand because I just asked you to get the S. Was it?
Yeah.
Yeah. Fine, so we'll write both answers down. What did you get when you used the S?
DS 18.26.
Or, and if you use the other formula?
192688. 0.2688.
So that's a difference of 1 degree. Technically, which is more accurate?
The angle?
Probably using the S.
No, the
Oh,
19.3.
Because the S is different.
Yeah, because what's happening here is these S's aren't actually the same. Slightly different. Now, did anyone feel like they got n max? No. Now let me show you how this is done, right? Look, n lambda equals d sine theta. So that means n is equal to d sine theta over lambda. But what is the biggest sine theta could be? 1. Yeah, when you use 90 degrees. So this must be less than d over lambda. It has to be. So it means the maximum value will be d over lambda. Now, can you calculate that, please?
6.0606. Yeah, 6.06.
So what you're saying is,
The N maximum.
n, no, just wait a second, sorry, n must be less than 6.06. So therefore, the maximum is 6. Now, if the answer was 6.96, what would you say the n max is?
7.
No,
Oh, it's still
6.
It has to be less.
It has to be less than it.
Oh,
Yeah.
could you say 6.5?
No.
Because lambda is an integer.
N is an integer, yeah. The answer is 6 here. So then lastly, what's the L here? The L here would be 12s, which is roughly 3 meters, I think. Isn't it?
Maybe, what was that?
0.33.
4 meters.
Oh, sorry. Oh, yeah. Roughly 4 meters.
So the N is like 6 and then
6 up, 6 down.
Oh, okay.
So he walked.
4 meters for this sound effect.
He heard nothing.
Yeah, so in other words, he's walking in the hall and then he picks up a faint sound. He continues to walk for 4 meters, experiencing this alternation, and then no sound.
Okay.
Is that alright? Is it?
Why the sine theta needs to be 1?
Why the what?
That's the maximum it can be.
Oh, the biggest value sine theta can ever be is 1.
Sine of
Ah, you need to talk to your maths teacher. Sine theta is never more than 1.
Zero and one.
Yeah.
Image.
The range, yeah. Okay. Continue. Do you need to write this down, or is all okay? You got it? Do you need to write? Maybe you need to write something down, no? You got that? Oh, I'm sorry, I still have to give you your physics results. I have to put them up on the notice board. I put the maths results up on the notice board. Forgot to put up the physics results.
Oh, maths result as well?
No, for my science students.
Mm.
I'll put your physics results up with your student number. Not today. Not today. Because what I'm going to do is have my lunch, then I have 3 more hours of teaching, then I'm going home. So it'll have to be tomorrow. Right, have you got that? Lynn?
Yeah.
Yep. Now, we have one more stinking big question to do. A diffraction grating has 300,000 lines per meter.
Slits.
Yeah. Red light with a wavelength of 633 nanometers is shone onto the grating, which is 1 meter from the screen. Alright, look, let's just do this together. Let's just be strong. Let's be both men/women about it, and we'll get through it. Okay. So obviously, such a question like this would be a section B question. Now, I promise you, it looks much worse than it is, and this is the hardest one I could make. So it's actually usually easier than this. It's the hardest one I could make. If Young's experiment came up as a section B question, it would look like this. Well, maybe there might be a part where it says explain what coherent means or something like that, but it's mostly like this. Okay, so I'll just draw the picture of what we have, alright? It's the usual story. You have a grate here, like this. You have a light source, you have a screen. The usual story. Okay, part A. Someone give me the idea here. What is the line spacing? That is, you have your diffraction grate. Can you see? There are 300,000 lines per meter. And I want the distances between each slit. How might I get that? 1 meter over 300,000. Can you bash that in and tell me what you get?
3.3 recurring times 10 to the minus 6 nanometers.
Minus 6 you said.
Oh, micrometers, yeah.
Okay? Are we okay with that? Are we sure? B. Determine the diffraction angle for the second order of red light. Which formula am I using? The first or the second?
The first.
First. Okay, second order. Right. Give me the formula. What's n?
2.
2. Do we know lambda?
Yes.
Well,
It's red light. Again.
it's given to us. 633. Nano. Equals d. Do we know d?
Yes.
Yes.
10 to the minus 6 sine theta. So can you get me theta? Of course you can. Please get me theta here.
Sine inverse 2 6 3 3 math error.
Math error.
23.344.
Nanometers times 10 to the 9.
22.344. What?
22 point.
3448.
Okay. Are we happy with that? Yes, continue. C. Determine the highest order of the red light. Well, we know the trick here, don't we? So we get n must be less than d over lambda. And what does d over lambda equal? 5.26.
Therefore, 5.
See, this isn't so bad so far, right? It's okay. Can I scroll down? D. Now we hit the hard part. The red light is replaced by blue light. And the blue light has a wavelength of 506.4. And it's found that the diffraction angle for some order of red light coincides exactly with the diffraction angle for the blue light in the next order. What the heck does that mean?
N2 equals N3. N3 red equals N3 blue.
That's it. That they're neighbours. The neighbour, well, we'll get to it in a moment. And I'll give you actually a little hint. So I'll just explain what's happening here. What has happened is you've put in now some blue light. So will n equals 0 be the same for the blue light?
Yes.
It will, won't it?
But N1 would be N2.
No, not necessarily. Now look, guys, no, stop doing stuff and look. Listen, unless you really understand what I just said there, do you? No, okay, so listen. Right, so, if I replace this with blue light, the blue light and the red light will be the same at n equals 0. But the angles will be different because the lambda is different. So maybe the n equals 1 is here. Maybe the n equals 2 is here. But what I'm saying is there'll be some place where the red and the blue will be the same again. And the relationship is that whatever the order is for the blue, it will be the same order as the red except one difference. So I give you a little hint. I say use x and x plus 1 for the orders of n. So there's some order x of the red that will be in the same place as order x plus 1 for the blue. But that only happens in one part of the screen.
So you just equalize the equation?
Yes, essentially just equalize the two. But we have to be really careful about how we equalize. So let's have a look here. So let's have a look at the red light first. What is the formula for, oh my goodness, red light? We have n. Now I want to make sure. Yeah, n, which I say we should call x. Lambda for the red light equals d for the red light and sine theta for the red light. Now, for the blue, you have x plus 1 lambda the blue light equals d for the blue light and theta for the blue light. However, this will be the same as this. It's the same experiment.
Yeah.
And if they hit the screen at the same point, then, yeah. So therefore, your job is to solve for x. X lambda red equals x plus 1 lambda blue. Now, what did I say the red light wavelength was?
633.
Nano. And what did I say the blue light was?
What was this?
506.4. The nanos cancel on both sides. So you have just this equation. Solve for x. Solve this for x. Off you go. Nice. So the fourth order of the red light is in the same spot as the fifth order of the blue light.
But that happens in two places, right?
Symmetrically, yeah. Okay. Continue? Yes, guys, is it okay to continue?
Mm-hmm.
E. Determine the diffraction angle for the blue light, the second order. Well, this is the same as what you did earlier, isn't it? In part B. Yeah. What do you get here?
For the second order.
Yeah, this is the same as this. You just need to change this to 506.4. Okay. So just change that to 506.4 and tell me what you get now. I'm looking at now for the blue light.
17.71.
Okay. F. The fringes were red in part A and then blue in part D. If the blue light was replaced by white light, what colour would the fringes be? So instead of using red and instead of using blue, if you use white light, what colour will you have on the screen?
Really white.
So white it's racist. No, not this. Any other
No,
answers?
I mean like as in like white light, as in they're completely white.
No.
I said pink.
No.
Red and white.
Is it also pink? No. No, you've taken away the red, you've taken away the blue, and you've put in a white light.
No, it's just
But that's
the
why I was
blue
asking,
light
like-
was replaced.
Okay, I'm sorry.
No.
Excuse me, Mr. Linguist. Both red and blue are replaced with white.
No, but it's
No,
just-
because you replaced the red with the blue, and now I'm replacing the blue with the white.
No, I'm just asking because.
Sorry,
you said
Zach
there
was just
no,
annoying me.
There's no way there's white light in this.
No, okay. You have white light, or practically white light. You use like the sunlight, for example. Remember what white light is. It is a mixture of all the colours. So having a white light source is like having all the colours coming out of one source. Now, look at the angles. What angle did you get when you used the red light?
18.3. No, 22.3.
What did you get when you used blue light? A bigger or smaller angle?
Small.
Small.
Imagine you had red and blue mixed together, whatever colour that makes. When they go through the diffraction grating, they will split at different angles,
Prism.
like a prism. What is going to happen is you will get the rainbow.
Spectrum, yeah.
And what will happen is the red light will be up higher slightly than
The blue light.
the blue light.
Ooh.
So in fact, what you'll get is a rainbow starting with red on the top, orange, yellow, green, blue, indigo and violet.
Wouldn't it be in one fringe though?
Yeah, in one fringe,
The whole spectrum.
the whole
in one
spectrum
fringe.
in one fringe. And like Diego said, it will look like a prism. Yeah? Okay, good grief. I cheated. What is the fringe spacing for red light? Did you calculate that yet? No.
633 times 10 to the 9 times. What is that?
1 meter, was it? No.
Um,
1 meter is the capital D.
1 over 3, 6.
this is for the red light.
Yeah.
0.19.
Now the reason I picked red light is so you can answer the last question here. How wide does the screen need to be?
That times 2s. S max, N max.
Times 2.
Yeah.
Mm.
2.
It's going to be n max times 2s. And that's going to be what, roughly 2 meters or something? 4, so this, what do we get for n max? 5, wasn't it? So this is equal to 10s, which will be 1.9. So 1
times
point,
20.
1.9 is a little tight to be using in real life, so you want a little bit of space. So you would perhaps recommend to someone that they use a 2 meter screen. Because if you use exactly 1.9, then your red will be right at the edge of the screen. So
You have to times by 20.
no, N max is 5.
But isn't it both ways?
Okay, well you can think about it like this. It's 2 times N max times S.
Which is
1.9.
Or won't the fringes be 5 on that and 5 on
Yeah.
that?
Yeah, 5 times 2, 10 times S. Why did I pick the red light? Because I want the most extreme colour at the edge of the fringe. The red one is the one that's spread out the most. The red is the one that's at the end. So you want to make sure that you get the red light in on the left and on the right. So a 2 meter screen would get the whole image. Nothing is lost. What's wrong, Zach? You look so unhappy with this.
Nothing.
Now are you thinking about lunch? Yeah, me too. Yeah? Yeah. Let me go back, yeah. Which letter?
D is looking for the second order of right, left, right. And
Yeah.
But for the last question, the question before this one.
F?
No, I mean
E?
the one we have all
G?
down. No.
Oh, this one.
Yeah.
This one.
And for the B, it's also looking for. Oh no, for C.
It's the same.
For the but why they didn't chance to.
For C?
Yeah.
C.
Yeah.
You did in times 2.
Yeah.
What do you mean? Show me.
So looking for the 19 degrees.
Oh, because in the formula, well, the 2 is there.
No, you said the answer is 19.
No, they said 19. I thought
Okay,
they.
so that's
I think that's wrong then, yeah. Guys, in the last one here, sorry, Gina was just asking me, what is the angle of the second order fringe? The formula is,
for N1.
N, you did it for N1. Oh, thank you for spotting that, Gina. N lambda equals D sine theta.
That was Diego giving the
Now,
answer.
hang on. Leave Diego alone.
Hey, these children.
Theta equals sine inverse 2 lambda over D.
Yeah.
So that is sine inverse, what was the lambda?
6.33 is minus 7.
What's the next question? man?
What was the lambda? Hang on, sorry.
The lambda was 0.
2 times 0.165.
Oh, no, yeah, sorry.
Diego, I'm going to strangle you. And what was the D here?
I think it was 1.
Yeah, you can type
No, it was 1 meter, wasn't it? Alright, so can you type that in and see what you get?
19.2688.
Is it?
Yeah.
Okay, I don't understand what's happening. What?
No, I just want to confirm that Diego was right. Okay, no, don't show me your fancy graphic calculator.
19.3.
Okay. Okay, you were right, Diego. The class doubted you, but I never
I
did.
know.
What? Wait, I don't understand what was the question. What were we checking?
We were just checking the answer for this one, part C.
Yeah.
Why?
I
Why?
just got a question.
Yeah.
Now,
It's just a question.
Because Gina just had a question, that's all.
Ah.
She didn't
No,
believe
I
Diego.
thought we
Diego.
did. I thought we did something wrong. Sorry.
He doesn't believe in your skill.
Yeah, I know.
You have a reputation problem, Diego. You have to work on it. You have to become more trustworthy.
That's gonna be hard.
It is, isn't it? Okay, are we okay with these 2 examples now? Yeah? So it's not madly difficult, because like I said, this is the most difficult one. So there's a few minutes left. You should be able, I don't know how many questions you have, you should be able to get a start on them.